Look up tonight, at the sky above you. Somewhere up there, hidden in places we usually cannot see, are objects that are too small to spot with any backyard telescope, and too heavy for the ground beneath them to exist. The closest one to Earth is hundreds of light years away, and it is still pulling on us, gently, through its gravity. Tonight, we're going to walk through what a neutron star actually is. We're going to look at how a star 10 or 20 times the sun's mass can fall into a ball you could fit inside a single city. We're going to examine the surface, where a mountain can only be a few millimeters tall before gravity flattens it. We're going to visit one that spins 716 times per second, faster than any kitchen blender ever built. We're going to visit one with a magnetic field a quadrillion times stronger than Earth's. And we're going to sit with the strangest question of all, which is what happens at the very center, where neutrons themselves may stop being neutrons. By the end of tonight, you will understand why even the scientists who study neutron stars describe them as objects that almost should not exist. So get comfortable. Let your hands rest. Let the room around you settle. Make something warm if you want it. We're going to take this slowly, the way it deserves. If you can, a subscribe before we begin helps these videos reach more people who like to think slowly. I appreciate it more than you know. Now, let's begin. The picture most of us carry, when we hear the words neutron star, is something close to a regular star. A glowing thing, far away, sitting in space, perhaps a little smaller or a little stranger than the stars we can name. The mind reaches for what it knows, and it offers back the closest thing in its memory. That picture is wrong from the very first frame. A neutron star is not a star in the way our sun is a star. The sun is a slow, steady ball of hot gas, churning through nuclear fuel, holding itself up against its own gravity by burning, second after second, for billions of years. A neutron star does none of that. There's no fuel left inside it. There's no fire. There's no slow burn. The light that comes off it is not the light of fusion. It is the light of something already dead and still glowing. What sits there instead is something almost unbearably small, and almost unbearably heavy, and almost unbearably calm. It is roughly 20 kilometers across. That is about the length of Manhattan. That is less than the distance between 2 metro stops in many cities. If you set a neutron star down on the surface of the Earth, in the middle of the largest urban grid you can imagine, it would not stretch from one neighborhood to the next. It would sit inside the boundaries of the city like a small black sphere, quiet, dense, and impossible. And yet inside that small sphere is more material than our entire Sunday. This is the first sentence in this video that the human brain refuses to hold properly. The sun is 1,000,000 times wider than the Earth. You could fit 1.5 million Earths inside the sun, with room to spare. The sun is not a small object. It is not a light object. It is the central, defining mass of our solar system, the thing every planet orbits, the thing every comet bends toward. Now take all of that and squeeze it into something the size of a city. That is a neutron star. The word neutron tells you what is inside, not the gas of a normal star, not the gentle hum of hydrogen and helium. Inside a neutron star, the protons and electrons that make up ordinary matter have been pressed so hard by such impossible gravity that they have merged into each other and become neutrons. Neutrons stacked next to neutrons. Neutrons crushed against neutrons. Neutrons all the way down. The whole star is essentially one giant atomic nucleus. That is the second sentence the brain refuses to hold. An atomic nucleus is a thing that lives inside a single atom, smaller than 1/1000th of a meter across, the kind of scale you cannot see with any microscope ever built. A neutron star is, in some sense, an atomic nucleus the size of a city. The room you are in right now contains an unimaginable number of atoms, each with a tiny nucleus inside it, surrounded by mostly empty space. Take all that empty space out. Pack the nuclei together until they touch. Keep packing. Keep packing. That is the density we are walking toward tonight. And we are not even at the strangest part yet. The strangest part is the way these two facts sit together. The size and the mass. They do not belong in the same sentence, and yet every neutron star in the universe is exactly that sentence. 20 kilometers across. More than the entire sun, packed inside. If you try to draw a picture of this in your head, the picture quietly comes apart. The brain is good at scale when scale is roughly familiar. A house is bigger than a person. A mountain is bigger than a house. A planet is bigger than a mountain. A star is bigger than a planet. The numbers grow, but the relationships stay the same. Bigger thing, more material. Smaller thing, less material. A neutron star breaks this rule. The size is small. The material is huge. And the relationship between size and material is no longer the relationship you grew up with. This is what we are going to keep returning to tonight. Every fact in this video is, in some way, another version of this same paradox. The object is too small to see, and too heavy to lift. The object is the size of a city, and the weight of a sun. The object is right there, and the object is impossible. To understand how this can be true, you have to let go of the picture you started with, and let a new one form slowly, in its own time. The new picture is not really a star. It is a remnant. It is what is left over when something much bigger has died. Imagine a star 8 or 10 or 20 times more massive than our sun. A blue-white giant, hot, fast-burning, much shorter-lived than its smaller cousins. Such a star spends a few million years burning through its hydrogen, then its helium, then its carbon, then heavier and heavier elements, working its way down the periodic table inside its core. Each new fuel burns hotter and faster than the last. The star is racing through its own life, and it does not know it. Eventually, the core of that star starts producing iron. Iron is where the running stops. Iron does not give energy when you fuse it together. Iron takes energy. The moment a star's core fills up with iron, the engine that has been holding it up for millions of years quietly shuts off. Then the inside of the star starts to fall. Not slowly, not gracefully. The core of the star, which was the size of the Earth 1 moment ago, collapses on itself in less than a single second. The outer layers of the star, which were millions of kilometers across, suddenly find that nothing is holding them up anymore. They fall too. What happens next is one of the most violent events the universe is allowed to produce. The infalling layers slam into the collapsing core, bounce off, and tear the star apart from the inside. A supernova. For a few weeks, this single dying star outshines the entire galaxy it lives in. But the supernova is not the part we are here for tonight. The part we are here for is what is left behind, in the very center, after the explosion has rolled away. A small, hot, impossibly dense ball of crushed matter. The core of the dead star, squeezed by its own collapse into something only a city wide. A neutron star, born in a single second, out of a process so violent it can be seen from other galaxies. And yet, when the dust settles, the thing it leaves behind is small enough to hide. That is what we're looking at when we look at a neutron star. Not a star. A grave. A grave the size of a city, holding the weight of a sun. To really understand the kind of object this is, it helps to walk slowly through the death itself, and what it does to ordinary matter. When the iron core of a massive star finally fails to support its own weight, the collapse is not gentle. The center of the star is suddenly racing inward at thousands of kilometers per second. The temperature climbs past 5 billion degrees. At those temperatures, the iron atoms themselves cannot survive. The high-energy radiation inside the core tears them apart, breaking iron back down into smaller pieces, into helium, into protons and neutrons. This is called photodisintegration. The core is disassembling itself. Then something stranger happens. The pressure becomes so high, the gravity becomes so steep, that the electrons in the core are pressed against the protons until they merge. An electron and a proton, pushed close enough together, combine into a neutron. The reaction releases a tiny ghost particle called a neutrino, which streams away from the dying star at nearly the speed of light. In a matter of seconds, almost every electron and proton in the collapsing core is converted this way. The protons disappear into the neutrons. The electrons disappear into the neutrons. What was once a complicated mixture of particles is becoming a single substance, made almost entirely of neutrons. This is where the name comes from. Neutron star. A star that has shed almost everything except its neutrons. While this conversion is happening, the collapse is still going. The matter is being crushed inward, faster and faster, and the only thing that can stop it now is something physicists call neutron degeneracy pressure. It is the same kind of pressure that keeps the electrons in your body from passing through one another. At a certain density, neutrons simply refuse to be packed any closer. They push back hard. When the inward fall meets that pushback, the collapse stops. Suddenly, the infalling outer layers of the star, which have been racing toward the center, slam into the now rigid neutron core and bounce. That bounce, combined with the wave of neutrinos pouring out of the core, blows the rest of the star apart, the supernova. But the core itself, the thing that finally said no, is now a sphere of neutrons, about 20 kilometers across, holding more than a sun's worth of mass. The whole process, from the iron failing to the neutron core forming, takes less than a second, less than the time it takes you to take a single breath. The sun has been burning steadily for more than 4.5 billion years. The neutron star at the center of a supernova is born in less than a second. This contrast is part of what makes neutron stars so disorienting. They are old in one way and brand new in another. The atoms that made them have existed for billions of years. The crushed core they have become took less than a heartbeat to form. And once it is formed, it does not change very much. The neutron star sits there, in the middle of the wreckage of the supernova, slowly cooling, slowly spinning, slowly leaking energy into space. It does not burn. It does not grow. It does not collapse any further. It is, in some sense, finished. A finished thing. A finished thing the size of a city. Hold that picture in your head. We're going to start zooming in. The first number that breaks the brain, when you start zooming in on a neutron star, is the weight of a single teaspoon of its material. Take a normal teaspoon, the kind you stir sugar into tea with, about 5 milliliters, about the volume of a small marble. Now imagine, just for a moment, that you could reach down to the surface of a neutron star and scoop out exactly that much material. That teaspoon, if you could lift it, would weigh roughly 1 billion tons. Not 1,000 tons. Not 1,000,000 tons. 1 billion. The number alone is not enough to feel. Numbers this big slide off the brain. So let us walk it down into something we can hold. 1 billion tons is more than every car ever built on Earth, combined, and stacked on a single point. It is more than every cargo ship that has ever crossed every ocean, rolled into one. It is roughly the weight of a small mountain, packed into something the size of a single sip of tea. If you had that teaspoon in your kitchen, and you let go of it, it would not fall to the floor. It would fall through the floor. It would fall through the next floor. It would keep falling, accelerating, melting and burning and tearing through every material the Earth is made of, all the way down through the crust, through the mantle, through the outer core, until something finally caught it. It would behave less like a piece of matter and more like a small, deliberate hole in the world. This is what 1 teaspoon of neutron star material would do. And the entire neutron star is not a teaspoon. It is 20 kilometers wide. The whole object is made of this material, packed tightly together, all the way through. This is the density we have been walking toward. The official number, the one written in physics textbooks, is around 10 to the 17 kilograms per cubic meter. That is a 1 followed by 17 zeros in kilograms in every cubic meter. For comparison, the densest naturally occurring metal on Earth, osmium, sits at around 22,000 kilograms per cubic meter. The Earth itself, averaged out, is about 5,500 kilograms per cubic meter. Water is 1,000. A neutron star is roughly 100 trillion times denser than water. The cleanest way to think about this is not in numbers, but in pictures. Imagine taking the entire mass of the Earth, every continent, every ocean, every mountain, every blade of grass, every person, every animal, the whole planet, and squeezing it into a sphere about 300 meters across, the size of a single tall building. That is what a chunk of neutron star material, the volume of the Earth, would be like. Or take it the other direction. The sun has more than 1 million Earths worth of mass inside it. Squeeze that into a city. There is no good way to imagine this. The brain offers up very heavy, very small, and gives up. That is fine. Sit with the failure. The failure of the picture is part of the truth of the object. Some things in the universe were never meant to be imagined. They were just meant to be measured. To understand why neutron star material is this dense, you have to understand a small, quiet, almost forgotten fact about ordinary matter. Ordinary matter is mostly empty. The desk in front of you, the phone in your hand, the bones inside your fingers, all of these things, at the smallest level, are made of atoms. And an atom, when you look closely at it, is almost entirely nothing. In the center of an atom, there is a tiny nucleus. The nucleus is where almost all the mass of the atom lives. Around the nucleus, far away in atomic terms, there's a thin cloud of electrons. Between the nucleus and the electrons, there is empty space. A lot of empty space. To get a sense of how empty, imagine the nucleus of a single atom expanded to the size of a marble, sitting on the floor of a stadium. The electrons would be tiny specks, somewhere in the seats at the back. Everything in between the seats, the field, the lights, the air, all of that, in the real atom, is empty. You are made of atoms like that. So is the chair you are sitting in. So is everything you have ever touched. This is the secret of normal matter. It feels solid because the electrons of one atom and the electrons of another atom push each other apart. They do not let each other get any closer. But behind that pushing, there is mostly nothing. Now imagine taking all that nothing out. Imagine pressing the atoms together so hard that the electrons can no longer hold their distance. The electrons get crushed into the nucleus. The protons in the nucleus combine with them to form neutrons. The empty space disappears. The matter is no longer mostly empty. It is full. This is what gravity does inside a neutron star. It empties out the emptiness. Once the atoms have been crushed this way, what is left is essentially just the nuclei, all touching each other, packed wall to wall. There is no more space between them. There is no more cloud of electrons. There's no more atom in the way you and I would recognize one. There's just a single, continuous sea of neutrons. That sea is what makes the density possible. A neutron star is not denser than ordinary matter because its particles are heavier. The neutrons inside a neutron star are exactly the same neutrons that exist inside the atoms of your body. Right now, they are not new. They are not exotic. What is exotic is how close they are. In your body, your atomic nuclei are spread out across the empty cathedrals of their atoms, with vast empty halls between them. In a neutron star, those same nuclei are stacked against each other, edge to edge, with no halls and no empty space at all. The same particles, a different arrangement. That is the entire trick. The reason your hand cannot pass through your desk is not really because the desk is solid. It is because the electrons in your hand are pushing against the electrons in the desk. Take away that pushing, take away the electrons themselves, and what was once solid is suddenly mostly room. The desk would collapse. So would your hand. So would everything you have ever called real. A neutron star is what you get when that collapse has already happened and finished and become a stable object. A neutron star is not strange material. A neutron star is ordinary material with a lie of ordinary space taken out of it. That is why a teaspoon of it weighs 1 billion tons. The teaspoon is full. If the density is the first fact that breaks the brain, the gravity is the second. The gravity at the surface of a neutron star is not just stronger than Earth's. It is stronger than anything you have ever encountered, anything you have ever read about, anything you can comfortably imagine. The number you will see in the textbooks is something like 200 billion times the gravity at the surface of Earth. 200 billion. That is not a number the body can feel. So let us bring it back to the body. Right now, sitting where you are, the gravity of Earth is pulling on you with whatever weight you are used to. Your body knows this weight. Your bones support it. Your muscles hold you up against it. Your heart pumps blood up to your brain, against it. Every breath you take is a small negotiation with this gravity. You do not notice it because it is the only gravity you have ever known. Now imagine standing on the surface of a neutron star. You would not stand. There would be no standing. The first thing that would happen is that the atoms in your feet would be pulled toward the surface so hard that they would no longer be atoms. Your feet would not be crushed. Your feet would be erased. The structure of the matter that made up your feet would simply not survive the pressure of being a few centimeters closer to the center of the neutron star than the rest of you. The pull on your feet, in those few centimeters, would be unimaginably stronger than the pull on your head. This difference between how hard gravity pulls on one part of you and another part of you is called a tidal force. On Earth, the tidal force across your body is so small you cannot feel it. On a neutron star, the tidal force across the height of a human body is enough to stretch the body into a thin thread of atoms before the atoms themselves dissolve. The body would not arrive at the surface as a body. It would not even arrive as a human shape. It would arrive as a smear. This is one of those facts that sounds dramatic until you sit with it, and then it becomes quiet. The neutron star is not malicious. It is not violent. It is just there. The reason it does this to anything that approaches it is the same reason a pebble falls to the ground on Earth. It is gravity, doing the only thing gravity ever does, except more of it than the body has any way to translate. If you could somehow stand on a neutron star with some impossible kind of body that would not be torn apart, and you tried to lift your hand off its surface, you would not be able to. Lifting a single grain of sand on a neutron star takes more energy than lifting a battleship on Earth. A small jump, the kind a child does on a playground, would require the energy of a nuclear weapon. Walking, in the way you walk down a hallway, would simply not be possible. You would be flat against the surface, every atom of you, and gravity would not let you go. This is what 200 billion G feels like. The reason gravity is this strong on the surface is, again, the size and the mass. The mass is the same as the sun, more or less, but it is squeezed into a sphere only 10 kilometers in radius. Gravity, at the surface of any object, depends on how close you are to all of that mass. The closer you can get, the stronger it pulls. On the sun, you cannot get closer than the sun's surface, hundreds of thousands of kilometers from the center. On a neutron star, you are standing only 10 kilometers from the center, with the same kind of mass underneath you. That is the whole reason. Same weight, smaller distance, bigger pull. The pull is so big that it bends light. The pull is so big that the air, if there were any, would be compressed into a layer thinner than a sheet of paper. The pull is so big that the surface of the star, the part you would be trying to stand on, is not really a surface in the way you think of one. It is the top of a crystal lattice of crushed nuclei, packed so tightly that nothing can sit on top of it without becoming part of it. You cannot stand on a neutron star. You can only become one. There's a neutron star, about 18,000 light-years from Earth, in a crowded cluster of stars in the constellation Sagittarius. Its name is PSR J1748-2446 AD. Astronomers do not name these objects warmly. The name is just coordinates, but the object itself is one of the strangest things in the galaxy. PSR J1748-2446 AD spins 716 times every second. That is the fact. Take a moment to let that land. The object is the size of a city. It is a city-sized ball of crushed matter, holding more than a sun's worth of mass, and it is rotating around its own axis 716 full turns in a single second. To put that in something human, the fastest blade of a kitchen blender turns a few hundred times per second. The fastest dental drill, the kind a dentist uses, also tops out somewhere in that range. PSR J1748-2446 AD turns faster than either of those. And it is not the size of a blender blade. It is the size of a city. If you were standing at the equator of this neutron star, somehow, with some impossible body, you would be moving sideways at roughly 70,000 kilometers every second. That is around 24% the speed of light, almost a quarter of the speed at which the universe lets anything move at all. The Earth's equator, by comparison, moves at about half a kilometer per second. The Earth takes a day to turn once. PSR J1748-2446 AD turns more than 700 times in a second. If the Earth ever spun that fast, it would not survive. Its rocks would not hold together. Its oceans would fly off into space. Its surface would be ripped outward by centrifugal force long before any of those things had time to happen. The fact that PSR J1748-2446 AD does not fly apart, that it holds itself together while spinning at this speed, is itself a measure of how strong its gravity is. Gravity is the only thing keeping this object whole. Gravity, on a city-sized ball, holding it together against a rotation that would tear apart anything else. This is one place where neutron stars start to feel almost alive. When astronomers detect a neutron star, they often see it as a pulsar. A pulsar is a neutron star with a strong magnetic field, tilted away from its rotation axis, sending out beams of radiation from its magnetic poles. As the star spins, those beams sweep across the sky like the lights of a lighthouse. If one of those beams happens to cross the path of Earth, we see a pulse, then nothing, then a pulse, then nothing, on the same regular rhythm as the star's rotation. For PSR J1748-2446 add, that rhythm is 716 pulses per second, a flicker too fast for the human eye to follow. A pulse that arrives at Earth, after 18,000 years of travel, still beating with the precision of an atomic clock. These objects are some of the most accurate timekeepers in the universe, more accurate, in some cases, than the best clocks ever built by human beings. Astronomers use them as cosmic timing references, the dead core of an exploded star, spinning hundreds of times a second, telling time more precisely than anything we have built ourselves. There's something quietly humbling about that. The fastest, steadiest clock in our galaxy is a corpse the size of a city, turning 716 times every second, in the dark. And there are many of these. Pulsars are scattered throughout our galaxy, spinning at all kinds of speeds, some slow and stately at one rotation every few seconds, some fast and frantic, like PSR J1748-2446 add. Each one is a small radio lighthouse, sweeping its beam through space, marking time on a clock that started ticking the moment the original star died. The universe is full of these. Most of them we have never heard from. We see only the ones whose beams happen to cross our line of sight. The rest are out there, spinning silently, ticking off the seconds of their long, dead lives. There may be hundreds of millions of them in our galaxy alone, most of which we will never directly detect. A galaxy of corpses, all keeping perfect time. If PSR J1748-2446 add is the spinner, then the next neutron star we're going to meet is the magnet. In the constellation Sagittarius, on the far side of our galaxy, about 42,000 light-years from Earth, there is an object called SGR 1806-20. It is a particular kind of neutron star, a kind called a magnetar, and it carries the strongest magnetic field that has ever been measured anywhere in the universe. Earth's magnetic field, the one that protects us from the solar wind, is small, less than a single Gauss, by the unit physicists use to measure these things. The sun's magnetic field is a few Gauss in most places, with stronger pockets and sunspots. A refrigerator magnet, the kind that holds a note to your kitchen wall, is around 50 to 100 Gauss. A medical MRI machine, the strongest magnetic field most people will ever stand inside, is somewhere around 15,000 Gauss. A typical neutron star already has a magnetic field of around 1 trillion Gauss. 1 trillion. Already. A normal neutron star is a magnet on a scale that no human technology approaches. A magnetar is a neutron star whose magnetic field is 1,000 times stronger still. SGR 1806-20 has a magnetic field of around 10 to the 15 Gauss. A quadrillion Gauss. 1,000 million times the strength of an ordinary refrigerator magnet, sitting there, pinning a forgotten note to a forgotten kitchen. These numbers are useless until you put them next to a body. So, a magnetic field of this strength, if you brought a human body anywhere close to it, would not just affect the body, it would unmake the body at the level of its atoms. The shape of every electron orbital in your body depends on the strength of the surrounding electromagnetic forces. In a magnetic field of 1 quadrillion Gauss, those orbitals to form. Atoms become long, thin, cigar-shaped structures, stretched along the direction of the field. The chemistry that holds molecules together stops working. Water stops being water. Proteins stop being proteins. This would happen to a body long before it reached the surface of the magnetar. Estimates suggest that within about 1,000 kilometers of one of these objects, the magnetic field is already strong enough to pull a body apart by its electromagnetic structure. Closer in, the field becomes one of the dominant forces in physics, capable of changing how light itself moves. In a strong enough magnetic field, the empty vacuum of space stops behaving like empty space. The vacuum becomes optically active. Light passing through it bends and splits in ways it never does anywhere else. Near a magnetar, the laws of physics that we use here on Earth are still the same laws, but they show a face we never see in our gentle corner of the universe. On December 27, 2004, SGR 1806-20 did something that briefly affected our planet from 42,000 light-years away. It produced a giant flare. In 1/10 of a second, this single distant object released more energy than the sun has emitted in the past 100,000 years. Read that again slowly, if you need to. 42,000 light-years away, across the entire width of our galaxy, through clouds of dust and gas and intervening stars. The flare from SGR 1806-20 still arrived at Earth strong enough to be detected by spacecraft, strong enough to slightly disturb the upper atmosphere of our planet, strong enough to register as one of the brightest gamma-ray events ever recorded by human instruments. If a flare like that happened from a magnetar within a few light-years of Earth, it would damage our atmosphere severely. It would destroy a meaningful portion of the ozone layer. It would cause significant biological damage on the surface. Fortunately, no magnetar is anywhere near that close to us. The nearest known one is around 9,000 light-years away, and it is, by all current measurements, quiet. But the universe is large, and there are many magnetars, and they have been flaring across deep time, long before there was anyone to notice. This is one of the things sleep does not always let us think about. The universe has been doing this kind of thing for billions of years. Stars dying, cores collapsing, magnetars flaring, light traveling for tens of thousands of years to reach instruments that did not exist until the last few decades. We are catching the ends of these stories, the very last frames, the faint pulses, the brief flickers, the gamma-ray echoes of events that finished happening long before the first cell on Earth divided. A neutron star is not a story we are telling ourselves. It is a story the universe was already telling, long before we arrived to listen. There's a fact about neutron stars that is small in numbers and very large in feeling. The tallest mountain on a neutron star can only be a few millimeters tall. That is the whole fact. A few millimeters, the thickness of a few coins stacked on top of each other, less than the width of a fingernail. That is the absolute maximum height that anything can rise above the surface of a neutron star before its own weight crushes it down again. This is what gravity does to topography. When gravity is strong enough, on Earth, mountains can rise nearly 9 kilometers before the weight of the rock starts to flow plastically and limit any further height. Mount Everest is roughly at that limit. The reason Earth does not have mountains 30 kilometers tall is that the rock at the base of such a mountain would be crushed under its own weight, and the mountain would slowly sink back into the planet. The same principle applies to a neutron star. There is a maximum height of feature can rise before its own weight overcomes the strength of whatever it is made of. On a neutron star, that height is millimeters. Imagine standing on a perfectly smooth ball, 20 kilometers across, with no real hills, no real valleys, no real surface features at all. Just a slightly uneven crust, with bumps the height of a coin and dips the depth of a coin. That is what a neutron star looks like, geologically. The crust itself is strange. Astronomers and physicists believe it is made of a kind of crystalline lattice of atomic nuclei, mostly iron at the very top, packed in a regular pattern, with electrons moving freely between them. Beneath that crust, the structure changes again. The nuclei become more neutron-rich, deeper down. Eventually, the boundary between separate nuclei dissolves, and the matter becomes a uniform sea of neutrons. This crust, despite being thin, is incredibly strong. The lattice of nuclei is held together by forces orders of magnitude stronger than the forces that hold ordinary metals together. The crust of a neutron star is, by some measures, the strongest known material in the universe. Stronger than diamond, stronger than any alloy, stronger than any bonded substance human beings have ever produced or imagined producing. And yet even this material, the strongest substance the universe makes, can only support a mountain a few millimeters tall. That is how strong the gravity is, that even the strongest possible material can barely lift itself a finger's width off the surface. When astronomers detect what they call a starquake on a neutron star, what they are usually detecting is the crust adjusting. The interior of the star is in a slightly different rotational state than the crust, and tension builds up over years or decades. Eventually, that tension snaps. The crust shifts. A piece of it cracks and rearranges itself by, perhaps, a fraction of a millimeter. That tiny shift releases enough energy to flicker across our galaxy. Some of the brightest single events in our sky, gamma-ray bursts of certain types, are believed to come from these crust adjustments on faraway magnetars. A neutron star in a distant galaxy moves a fraction of a millimeter, and on Earth, billions of years later, a satellite picks up a flash that lasts a tenth of a second. This is the scale we are dealing with. A millimeter on a neutron star is an event. A whole mountain there is the height of a thumbnail. A whole geological adjustment there is the width of a hair. And those tiny motions are visible across the entire visible universe. The contemplative part of this, if you let it land, is that an entire planet's worth of geology, of structure, of change, is happening on these objects at scales we would never even notice on Earth. Our hills and valleys, our mountain ranges, our continental shifts, all of it would be invisible there. A neutron star is doing all of its geological living at the scale of a fingerprint. Quiet, slow, and unimaginably violent at the same time. That is what the surface of a city-sized star looks like. Smooth, except for the coin-thin mountains. Still, except for the millimeter quakes. Silent, except for the flashes that cross half a universe. When you spend enough time with neutron stars, the conversation slowly stops being about astronomy and starts being about matter itself, about what matter is allowed to do, about the boundaries between one kind of stuff and another. Almost everything you think of as different kinds of material on Earth is really just different arrangements of the same handful of particles. Wood and water and stone and air and skin all share the same building blocks. They are made of atoms. The atoms are made of protons and neutrons and electrons. The differences you feel between a piece of wood and a glass of water and the air in your lungs come from how the atoms are bonded, what elements they are, how loosely or tightly they pack together. A neutron star is what happens when you remove one of those degrees of freedom, when the bonding does not matter anymore, when the elements no longer matter, when the only thing left is the raw substance underneath everything, packed as tightly as it is allowed to be. What you find, when you go that far, is a kind of matter that does not exist on Earth, not in any laboratory, not in any extreme experiment, not even in the cores of the most powerful particle accelerators. The only place this kind of matter exists, in the entire universe, is inside neutron stars. That makes neutron stars laboratories. Strange, distant, untouchable laboratories. When physicists try to write down the equations that describe how matter behaves at extreme densities, the equations have several different solutions. Different theories say different things about what happens when you keep packing matter tighter and tighter. Some theories say neutrons stay neutrons all the way down. Some say that, at a certain density, the neutrons themselves break apart, and what is left is a soup of quarks, the smaller particles that normally live inside protons and neutrons. Some theories say there are even stranger possibilities at the very center, types of matter we have no clean name for. We cannot test these theories in any laboratory on Earth. The energies required are beyond anything we can produce. The densities are beyond anything we can compress. The only way to know which theory is correct, if any of them is to study the neutron stars themselves. Every measurement of a neutron star, of its mass, of its size, of how it cools, of how it spins, of how it reacts when it collides with another neutron star, is a small data point about how matter behaves under conditions we cannot recreate. In 2017, two neutron stars collided in a galaxy called NGC 4993, about 130 million light-years away. The collision sent a ripple through the fabric of space-time, a gravitational wave, that traveled for 130 million years and finally reached Earth. Detectors on this planet picked it up. Telescopes turned to the right part of the sky. They saw the afterglow. That collision, observed across many different kinds of light and through gravitational waves at the same time, told us things about the inside of neutron stars that decades of theory had been trying to guess at. It told us that the equation of state, the way matter behaves at neutron star densities, is somewhere between the soft theories and the stiff theories. It told us that the heavy elements in the universe, the gold and platinum and uranium, are largely produced in events like this: the wedding ring you wear, if you wear one, the gold filling in someone's tooth, the thin layer of gold inside the connectors of the device you might be using to listen to this. Most of those atoms were forged in the collision of two dead stars billions of years ago, and then scattered across space until eventually they settled into rock that became Earth. Hold that for a second. The metals that make up your jewelry are old, and the way only neutron star material is old. They were not made on Earth. They were not made inside the sun. They were made in the brief, blinding instant when two neutron stars hit each other, in some galaxy that no longer looks the way it did when the collision happened. You are wearing the wreckage. The whole story of what matter is allowed to do, and what stars are allowed to do at the ends of their lives, is sitting on your finger. When we study neutron stars, we are not just studying distant strange objects. We are studying the kitchens, where the heaviest atoms in the universe were cooked. The kitchens are violent. The kitchens are small. And the products of those kitchens are sitting all around you, quietly, in everything that contains anything heavier than iron. The universe makes its heaviest jewelry inside its smallest, densest, deadest stars, and then it spreads them out, slowly, across the dark. If you let yourself imagine, for a moment, what it would be like to actually approach one of these objects, the picture is unsettling and quiet, and not entirely something the body wants to hold. A neutron star is dark. Despite all the radiation it can produce, despite the magnetic fields and the X-rays and the radio pulses, the actual visible surface of a neutron star is not bright in the way the sun is bright. Most of the energy comes off in invisible wavelengths. To human eyes, an isolated neutron star, viewed from millions of kilometers away, would look like a small dim point, with a faint blue or whitish tint, no different at first glance from a faraway star. You would not know what you were looking at until you got closer. Closer is where the picture changes. Long before you reach the surface, your spacecraft, if you had one, would start being affected. The magnetic field, even for an ordinary neutron star, would begin to deform any electronics on board. The radiation, even from a quiet pulsar, would be enough to fry sensitive instruments. The gravity, well before you reach the actual star, would begin to stretch the spacecraft along its length. Closer still, and the gravity becomes the dominant fact about your existence. Your speed, falling toward the star, would be enormous. The light leaving the surface of the star, the light from behind it, the light from anywhere, would start to bend in ways that do not happen anywhere else in the everyday solar system. The horizon ahead of you would not look like a horizon. It would look like a sphere, with the sky around it folded inward. If you reach the height of about 10 or 15 kilometers above the surface, which is roughly equal to a single neutron star radius, the gravity would already be tearing apart anything made of ordinary matter. The structure of the spacecraft would not survive. Your body, if it were somehow there, would not survive. But suppose, for the sake of imagination, that the spacecraft and the body could last another second. Suppose you were close enough to look down at the surface of the neutron star, in the very last moment before you arrived. What you would see is not a planet. There are no continents. There are no clouds. There is no horizon, in the usual sense. You would see a smooth, faintly glowing crust, slightly speckled, slightly uneven, with millimeter-scale bumps and ridges that are the only landscape this object will ever have. You would see, if the magnetic field were strong enough, faint lines of plasma curving up out of the surface, following the magnetic field lines, like fine hair lifted by static. You would see, around the edges of the visible disk, the strange optical effect of gravitational lensing, where the back of the star itself is bent into view, even though it is on the other side. A neutron star, seen up close, is one of the few objects in the universe where you can literally see all the way around it, at once. The light from the back of the star is bent by gravity hard enough that it ends up coming toward you, around the edges, just before it would have escaped. You would see the entire surface, simultaneously, like a wrapped image draped on a sphere a little larger than the actual sphere. The brain, again, will refuse this picture. Things in our normal experience have a front and a back. Things in our normal experience hide behind themselves. Neutron stars, from up close, do not hide. The gravity does not let them. This is one of the more contemplative facts about these objects. A neutron star, in some optical sense, has no other side. You can see all of it. If you could survive looking at it, which of course you cannot, you would be looking at one of the few things in the universe that does not turn its back on you. It just sits there, spinning, glowing faintly, bending the light around itself, showing all of itself, all of the time, to anyone who happens to be looking. Even though almost no one ever is, the light bending is worth sitting with for another minute. It is one of the strangest, most beautiful consequences of the gravity around these objects, and it is something the brain does not naturally include when it pictures a star. When light leaves a hot object, in everyday experience, it travels in a straight line. The flame on a candle sends light out in all directions, and that light reaches your eyes by going from a flame to your eye, in something very close to a perfectly straight path. Near a neutron star, light does not travel in a straight line. Gravity, in Einstein's picture of it, is the bending of space-time itself. The denser something is, the more it curves the space around it. Around a planet like Earth, this curvature is slight. Around the Sun, it is enough to detect, but only if you are looking carefully. Around a neutron star, the curvature is dramatic. Around a black hole, it is total. A neutron star sits a step away from being a black hole. In this sense, the gravity is severe, but light still escapes. Just not in straight lines. A photon leaving the surface of a neutron star at an angle close to vertical will travel out into space, in something close to a straight path. A photon leaving at a more glancing angle, however, will be pulled back inward by the gravity. Some of these photons, the ones that came off the back of the star, follow curving paths that wrap around the star's surface and end up traveling back toward the side facing you. This is why you can see the back of the star. If you are standing in front of a neutron star, the photons that come off its near surface arrive in mostly straight paths. The photons that come off its far surface are bent around the star and arrive at your eyes from off to the side, slightly delayed. Both sets of photons end up reaching you. Your eye combines them. The image you see is not the image of one face of the star. It is the image of more than one face at once. The brain has nothing in everyday life to compare this to. There is no terrestrial object that lets you see its other side simply by looking. Even a transparent glass shows you what is behind the glass, not the back of the glass itself. A neutron star shows you its own back. For a star spinning 716 times per second, this means the surface visible to you at any given moment is changing, shifting, sliding around itself in ways that make no sense to ordinary perception. Hot spots on the surface, the kind that produce the lighthouse beam of a pulsar, can be visible from Earth even when they are technically pointing away. The geometry of what you can see near a neutron star is not the geometry of the world you live in. There is one more piece of this picture. Time itself runs slightly differently near a neutron star. This is not science fiction. This is measured. A clock placed near the surface of a neutron star would tick more slowly than an identical clock placed far away. The closer you are to a strong gravitational field, the slower your time runs from the perspective of someone safely outside the field. The effect near a neutron star is small but real, roughly 20 to 30% slower at the surface, depending on the mass and the radius. Not the kind of effect that ruins a wristwatch on Earth, but the kind of effect that, if you spent a year on the surface of a neutron star, would mean about 15 months of clock time had passed for everyone you left behind. You would return younger than the people who waited for you, by a meaningful amount. This is not a paradox. This is just what gravity does when you turn the dial up far enough. Time on Earth also runs slightly slower than time on a satellite high above the planet. The difference is so small that GPS systems have to correct for it constantly, but it is there, in the data, easy to measure. Near a neutron star, the dial is turned up so far that the effect becomes a substantial part of life. A clock on the surface, a clock in orbit. The clocks disagree. They cannot help it. This is one of those facts that does not feel comfortable. The flow of time, the steady forward march of things, is something the body trusts. It is the most reliable thing in your day, after gravity itself. Everywhere you have ever been, time is run at the same rate. Near a neutron star, it does not. The same seconds, the same minutes, the same hours slow down for you while the rest of the universe carries on. A neutron star is not just a place where the matter is different. It is a place where the time is different. A small, dense, dark object, sitting in space, gently bending light and time around itself. A whole different rule book, balanced on the head of a pen. In the constellation sextants, somewhere between 3 and 6,000 light-years away, there's a neutron star called PSRJ 0952-0607. Astronomers measured its mass carefully in 2022. The number they got back changed how physicists think about the upper limits of these objects. PSRJ 0952-0607 is, as best we can tell, the heaviest neutron star ever measured. Its mass is about 2.35 times the mass of the Sun. That number sounds modest, after everything we have already covered. The Sun, multiplied by a little more than 2. But the modest number hides something more interesting. PSRJ 0952-0607 sits very close to a theoretical ceiling, a limit beyond which neutron stars are not believed to exist. Above that ceiling, gravity overwhelms even neutron degeneracy pressure, and the object collapses further. It becomes a black hole. The ceiling has a name. It is called the Tolman-Oppenheimer-Fokoff limit, after the physicists who first worked it out. The exact value of the limit depends on details about how dense matter behaves, and those details are still being worked out. But the rough answer is that, somewhere around 2¼ to 2½ solar masses, a neutron star can no longer hold itself up. It crosses a line. It becomes something else. PSRJ 0952-0607 is sitting right at that line. If the original star that produced it had been a little heavier, or had collapsed a little more, the result would not have been a neutron star at all. It would have been a black hole. This is one of the more contemplative facts about these objects. There's a category beyond them, into which they can tip, if they grow too heavy. There is no equivalent category for ordinary stars. The Sun is not in danger of becoming any other kind of object. In the next few billion years, it will become a red giant, then a white dwarf. That is its path. The line it walks is a long, slow, simple one. A neutron star is different. A neutron star is, for its entire existence, sitting near a cliff. The cliff is the upper mass limit. The cliff is the threshold beyond which it stops being a neutron star and becomes a black hole. Some neutron stars, like PSRJ 0952-0607, are right at the edge of the cliff. Others are well back from it. None of them are far away from the idea of it. A neutron star is also dangerous to itself in another way. If it gobbles up matter from a companion star, which some of them do, that matter falls onto the surface and adds to the mass. Slowly, over millions of years, a neutron star with a companion can grow heavier. Some of them eventually grow too heavy. PSRJ 0952-0607 is one of these. It is in orbit around small companion star, and astronomers believe that, over a long stretch of time, the neutron star has been pulling material off that companion. They call it a black widow pulsar, a poetic name for the way it slowly consumes its partner. Over hundreds of millions of years, this pulsar has grown into the heaviest one we have ever measured. It may keep growing. Eventually, if it crosses the line, it will simply stop being a neutron star. In a single instant, it will collapse the rest of the way, swallow its own light, and become a stellar mass black hole. The transition would not be visible from Earth in any obvious way. The radio pulses would stop. The X-ray signal would disappear. The lighthouse beam would go dark. Astronomers would notice that the pulsar that had been there for decades was no longer there. The conclusion would be drawn carefully, quietly, in papers that would arrive months later. Another neutron star, gone over the cliff. Another small dead object, replaced by an even smaller, even darker object, pulling at the universe with the same gravity, but no longer letting any of itself out. There are, by current estimates, hundreds of millions to perhaps a billion neutron stars in our galaxy alone. Some fraction of those are sitting near the cliff. Some fraction of those will, in time, fall over it. The galaxy is slowly, century by century, converting its heaviest neutron stars into black holes, one quiet collapse at a time. The universe is doing this everywhere. Right now, while you are sitting in this room, there's one part of a neutron star that we have not really touched yet, and it is the part nobody has ever seen. The part nobody can see. The center. We know the surface. We know the crust. We know roughly how the upper layers of crushed nuclei give way to denser layers below. But somewhere down there, deeper into the star, the matter changes again, and the deeper it goes, the less certain anyone is about what is happening. At a few kilometers below the surface, the structure of separate nuclei dissolves entirely. There is no more lattice. There is no more crust. There is just a uniform sea of neutrons, with a small admixture of protons and electrons mixed in. This is sometimes called the outer core. Even here, the conditions are far beyond anything any human has ever directly examined. But the inner core is where the questions get harder. In the deepest part of a neutron star, where the pressure is highest, where the density climbs even further, the neutrons themselves may not be able to remain neutrons. The particles that make up neutrons, called quarks, may break free. The matter at the very center of a neutron star may stop being neutron matter and become something else. A soup of free quarks, perhaps, or a stranger soup of particles that contain heavier quark types found nowhere else in nature. Some physicists think this is what is happening in the cores of the heaviest neutron stars. Others think the neutrons hold together all the way down. Others think there is some intermediate state where the boundary between neutrons and quarks is fuzzy. The honest answer today is that nobody fully knows. This is one of the few places in physics where a question this fundamental still has multiple competing answers. The reason it is so hard to settle is that we cannot get at the inside of a neutron star. We can only get at it indirectly, through the way it affects the outside. By measuring how much mass a neutron star can hold before collapsing, we constrain the kinds of matter that could be inside. By watching how neutron stars cool over time, we constrain the heat-carrying particles that must be in the core. By detecting gravitational waves from neutron star collisions, we constrain how the matter behaves when it is squeezed even harder. Each of these measurements is a small probe, a thin needle, pushed down through layers of neutron star material that no human will ever touch. We are reading the inside of a city-sized object from billions of kilometers away by the way its outside flickers. This is one of the more humbling parts of modern astronomy. There are objects we know exist. There are objects we know are common, scattered through every galaxy. There are objects whose surfaces we can study, and whose pulses we can clock to the millisecond. And the deepest interior of those same objects we may never directly understand. The center of a neutron star is one of the few places in physics where a serious, central, important question simply has no settled answer. Not because nobody is trying, not because we lack the equations, because the conditions are so extreme that no laboratory in the universe, except the inside of a neutron star itself, can produce them. We will keep watching them. Telescopes will keep getting better. Gravitational wave detectors will keep listening for the quiet ripples that come when two of these objects collide. Slowly, over decades, the picture of what is inside a neutron star will sharpen. But for now, the very center of these objects remains a small, dense, contested mystery. A mystery the size of a kilometer, wrapped inside an object the size of a city, itself wrapped in a galaxy of other quiet objects, all keeping their own secrets in their own dark interiors. There's one last fact about neutron stars worth carrying with you before we slow down and turn back toward the opening. There are a lot of them. Estimates of the total number of neutron stars in our own galaxy, the Milky Way, range from hundreds of millions to perhaps a billion. The Milky Way is one galaxy out of several hundred billion. Every large galaxy is thought to contain a similar number of neutron stars. Spread across the visible universe, the total number of these objects is staggering. Many of them are detectable. Many of them are not. The ones we can see are usually visible because they are still pulsing, still beaming radiation our way, still in some kind of binary system that highlights their existence. The rest are silent. They have cooled past the point of being easily seen. Their beams have either turned in some other direction or weakened with age. They simply sit there, in the dark, in the spaces between brighter stars. If you go outside on a clear night, far from city light, and look up, you are looking at a sky that contains many neutron stars. None of them are visible to the naked eye. They are too faint, even when they are pulsing. But they are there, hidden among the stars you can see, threading through the dark patches, where you can see nothing at all. The closest known neutron star to Earth is roughly 400 light-years away. That is reasonably close, in galactic terms. There may be closer ones we have not yet detected. There certainly are, if the population estimates are even roughly right. Somewhere within a few hundred light-years of you, in some direction, there is a small dark sphere, 20 kilometers across, with the mass of a sun packed inside, slowly spinning, gently glowing in radio frequencies, drifting through the galaxy in some long, lazy orbit. You will never see it. It is not for you to see, but it is part of the same galaxy you live in. It came from a star that died long before you were born. The atoms that make it up were once part of a brighter star, perhaps even part of an early supernova that helped seed our region of the galaxy with the heavier elements that eventually became the rocks of Earth, the iron in your blood, the calcium in your bones. You and the nearest neutron star share an origin story, in some loose sense. Both of you are the slow output of a galaxy that has been building heavy atoms inside its dying stars for more than 10 billion years. Both of you, in the very long view, are parts of the same project. Most of those heavy atoms ended up in dust, in planets, in the bodies of living things. Some small fraction ended up packed into the strange little corpses we have been talking about all night. The galaxy is full of those corpses. They are part of its furniture. They are quiet. They are dense. They are common. And they will outlast almost everything else here. When the sun has died, the neutron stars in our galaxy will still be cooling, still spinning, still passing through the long dark afternoon of cosmic time. That is the population. Hundreds of millions, perhaps a billion. Just here, spread invisibly through the same sky you are looking at when you look up tonight and find it ordinary. The sky is not ordinary. The sky is full of these. We started this video with a paradox. A neutron star is too small to see and too heavy to lift, and both facts are about the same object. Now, after all of this, the paradox is no smaller. If anything, it is larger. We have given it more sides. A neutron star is the size of a city, and it weighs more than the sun. A neutron star is the densest stable form of matter in the universe, and it is also the closest cousin to a black hole. A neutron star is a corpse, and it is one of the most precise clocks ever found. A neutron star is a place where time itself runs slower than it does anywhere on Earth, and a place where light bends so hard you can see the back of the object from the front. A neutron star is small enough to hide, and common enough that there are hundreds of millions of them in our galaxy alone. These facts do not cancel each other out. They sit next to each other. They make a single object that the brain cannot fully picture, and they do this honestly. Every contradiction in this video is a real contradiction in the universe, not a trick of language. The universe really does pack the weight of a sun into something the size of a city. The universe really does keep precise time on the corpses of dead stars. The universe really does grow these objects sometimes, until they tip over into black holes. The brain cannot hold all of this at once. That is fine. The brain was not built for objects like this. What the brain can do slowly is sit with the strangeness and let the strangeness become familiar in pieces. Tonight is one piece. There will be others. Other neutron stars, other measurements, other unanswered questions about what is happening at the very center of these dark, dense, distant things. The truth is that we live in a galaxy that is, in part, made of objects like these. The truth is that the elements in your body were forged, in significant part, in events involving objects like these. The truth is that, somewhere not far from you in galactic terms, there's one of these objects sitting in the dark right now, slowly turning, pulling on the universe around it, glowing faintly in wavelengths your eyes were never built to see. The galaxy is bigger than the picture we usually carry. The galaxy is stranger than the picture we usually carry. And neutron stars are one of the reasons. It is late, and we have gone a long way tonight. We have walked from the death of a massive star, through the collapse, through the surface of the corpse left behind, through the spinners and the magnets and the heaviest one ever measured. We have stood near the cliff that separates these objects from black holes. We have looked into the centers we will never see. You can let all of it settle now. You do not have to remember every number. You do not have to keep track of every name. The teaspoon, the city, the 716 turns a second, the quadrillion Gauss, the millimeter mountains, the billion-strong population in our quiet galaxy. All of it can slip away, and the only thing left can be the feeling. The feeling that the sky above you is more layered than it looks, that the dark places between the visible stars are not empty, that there are objects out there that almost should not exist, and yet do, and they're hundreds of millions, going about their long, slow, faintly glowing afternoons. Sleep well tonight. The neutron stars are still there, spinning quietly in the dark, perfectly indifferent to whether anyone is watching, keeping their own time, holding the weight of their old suns inside skins the size of a city. If this is the kind of video you would want again, a small subscribe before you drift off helps these reach more people who like to think slowly, late at night, about objects too strange to picture. Thank you for sitting through this with me. Good night.